السلام عليكم ورحمة الله وبركاته. We will continue our lecture. Let me share the slide. I hope you can see it now. All right. Sorry. Let me take you to the presentation mode. Yeah, in our previous class, we looked at we introduced the hydrodynamic equations of flow. Briefly mentioned about the continuity equation, energy equation, and the momentum equation. You are able to derive the continuity equation. Today we will look at the energy equation and the momentum equation, okay? And then look at some examples of the applications to real life problems. This is where we start. We derive the continuity equation. The most important thing here is that Q equal constant. That is the discharge flow rate, the same. The flow rate is the same. We know that the flow rate, which is in L cube over T, is given by AV. The area, cross-sectional area of flow, times the velocity, the fluid velocity. These two, when multiplied out, gives the flow rate. So if Q is constant, it means V1 equal A2 V2, and like that. Meaning at every section of the flow, the product of area and the velocity of flow remains the same. Okay. This we will utilize later. Okay, and this happens when you have Q to be constant, when you have steady flow. Okay? When you have steady flow, when the flow parameters do not change with time. Okay, and for this to be maintained, as we are going to see, because this has far-reaching implication for all flows in channel or open channels, particularly hydraulic structures. Okay, it means some section, as you may have practical flows, you may have the section reducing or enlarging, in which case the area or the cross-sectional area increase or decrease. Okay, then that means if the cross-sectional area increase or decrease, the velocity has to adjust in order to maintain the same discharge. Okay, let's take some simple instances. Let's take an instance whereby the cross-section area decrease. Let's say you have a flow through an opening, or let's say we are going to look at what is called Venturi flow, okay, in which flow is compressed, the cross-section area reduces and then it enlarges, okay? So this is, let's say, A1, A2, A3, okay? So for the same flow rate to be maintained in these three sections, section 2, okay? This is section 1, section 2, section 3, okay? At section 2 area, the cross-section area of flow has decreased. Okay, so what happens to the velocity? The flow is locally accelerated. Okay, the velocity increases to maintain the same discharge. Okay, and the area decreases, the velocity increases. Okay, to maintain the same discharge. Okay, and then at this end, when you have enlargement or when you have increase in the cross-sectional area of flow, it means the area increases. And when the area increases, in this case, to maintain the same discharge, the velocity has to reduce. Okay? So the flow is decelerated in this case. The flow is decelerated. Whereas within the throat, within this area or section, when you have reduction in the cross-sectional area, the flow it undergoes acceleration. It is locally accelerated. Okay, and this is all with a view to maintaining the same flow rate. Okay, the same flow rate. This we will even measure in the lab. Okay, we will perform all these experiments. We will look at flow deceleration and flow acceleration. Okay, let me what you writing. I had some sounds about me making some comments. Let me see what you. Okay, okay. Momentum like what we have taken in C233 also flow rate decrease. Yeah, momentum like what we did in fluid mechanics. Okay. In fact, we're going to derive it here and the equation because the energy equation is similar to the Bernoulli equation, which we also derived in fluid mechanics. Okay. Let me go back to the presentation mode. All right. So for most hydraulic structures, you realize that the flow rate is more often than not constant. Okay, you have usually a constant flow rate, but then the sections may not be maintained, may not be the same throughout. So you have flow acceleration and flow deceleration. Okay. Now, for the energy equation, according to Newton's law of motion, second Newton's law of motion, the net force acting on a fluid element in the figure 9.2 below equal to its mass times its acceleration, because the fluid element is in motion. Remember the second Newton's law of motion is referring to what happens to a body in motion that is acted upon by a system of forces. Okay, and the law states that the body will accelerate. Okay, and the net force acting on the body, the net force acting on the body that is accelerating is equal to mass times the acceleration. Okay, so in this case, the net force acting on a fluid element is equal to its mass times its acceleration. It is in motion, hence it possesses acceleration. Okay, so this we will briefly analyze and then derive the energy equation, and express the Bernoulli equation, and then apply it to solve a simple problem. Now, the forces acting on the element include the net pressure force. Okay, pressure force is acting on the fluid element. A fluid element here is usually water. Okay, so the pressure force, as we know, is also called hydrostatic force. Okay, the pressure force is synonymous with hydrostatic force. Okay, and it is compressive. Pressure force is always compressive and normal to the surface or to the cross section. So that's why you have the pressure force acting normally. Okay, normally to the cross section, okay, at 90 degrees on both points, because pressure is always compressive. Okay, it is always compressive and normal to the surface. Okay, it represents the normal stress in solid mechanics. Okay, and here we use P to denote the pressure force. Okay, in fluid mechanics we use P to denote pressure. Okay, but here in the notation we use capital P to denote pressure force or hydrostatic force acting on the fluid element. The forces acting are the net pressure force and the gravity force. Okay, the gravity force is simply the weight. Okay, because weight is the gravitational force acting on a body, and the weight, as we know, will always act vertically downward. But the channel is inclined. You can see the slope, which is 1, 2, S0. Okay, the slope is theta. The bed slope is S0. Okay, the bed slope is S0. So that will make the weight component, the weight is acting vertically downward, but because it is tilted, it will have components in the direction of flow, and it will have vertical component with respect to angle theta. Okay, this is in the direction of flow because this small angle is theta. So when you resolve W along this plane, you have W cos theta. On the horizontal plane, you have W sine theta. Okay, and then you have any other internal force, such as the friction acting along the surface of contact. Okay, you have friction force, subscript D, acting along the surface. Okay, in this case, the frictional force will usually be in form of, the shear force. Okay, the shear force will constitute the frictional force because here we have fluid element. Okay, hence we have viscosity as the major cause of the shear. Okay, so that is, the frictional force will be in form of the shear force. Okay, acting at the bottom, which is always trying to oppose the relative movement of the body. Okay, although frictional force is acting this way, you have the shear force acting in the opposite. The frictional force and the shear force will more or less be the same. Okay, now the pressure force, which is P, the pressure force will be given by the pressure times the area. Okay, and I don't know what do I, okay, if capital, let me use small p to represent pressure, then A is the area. So this is the definition of the pressure force. Okay, because pressure is the force acting per unit area. Okay, so then the force will now be, the pressure force will now be equal to pressure times the area. Okay, and pressure, as we have seen in fluid mechanics, okay, the gauge pressure is given by rho gh, and h in this case is y. Okay, then we multiply by the area. So that's why we have this one, P equal rho g a y, okay, which gives the pressure force. Okay, and what about the weight? Weight is simply if we go by the definition of unit weight, okay, which is gamma, okay, it's simply weight divided by volume, okay, and then from here we'll see that weight is now the unit weight times the volume, okay, and unit weight is given by rho g, okay, unit weight is given by rho g, and the volume here is simply going to be the cross-sectional area times the length, okay, which is ds, okay. So the cross-sectional area times the length ds. So that's why we have A delta S. Okay. So this is the weight component. Okay. So these are the forces acting, the net pressure force, the gravity force, and any other internal force such as friction acting along the surface. Now, the term for acceleration in the S direction is given by, because I said the fluid is accelerating, okay? It is in motion, hence it possesses acceleration. And acceleration from your dynamics is dv, okay, which can be splitted into ds dt or del s del t dot del v del s. See here, del s will cancel del s, and we will go back to del v del t. So we haven't done anything, okay? And del s del t, that's the change in distance with time, is v, isn't it? So we can represent del s del t with v, okay? And when v goes inside the differential, okay, we have half del v squared del s. It becomes half because when we differentiate del by del s of v squared, we will have what? 2v del v del s. So to take care of these two, that's why we divide by 2, okay? So that we have 1 over 2 del v squared by del s, okay? Now, this is the acceleration component, okay? And the net force acting on the body is given by ma, okay? And we know that weight is equal to mg, okay? So the mass, okay, is going to be weight over g, okay? So that's mass is now weight over g, and a is given by this term, 1 over 2 del v squared by del s, okay? So this is the ma. Now let's analyze the pressure force as well as the weight component, okay? From the figure above, the net pressure force, because when you add it, this is pressure P, this is minus, okay, because force is a vector quantity, so it's positive in the, if we take this to be the positive direction, okay, so this is minus, okay, so it's going to be P minus del P del S delta S, okay, so we will have the net pressure force, okay, be equal to this, and then this is the pressure acting, okay, this is the pressure, and then we multiply by the area. We multiply by the area to give the pressure force, okay, and when we multiply by the area, we have the volume now, okay. If we remember, I just mentioned that if you remember in fluid mechanics, unit weight is, sorry, the specific weight is W over the volume, okay. So now del A del S is the volume, okay. So the volume is going to be the weight over gamma. So volume is now equal to the weight over gamma, which is exactly what we have here. Weight over minus weight over gamma del P del S, okay. Now, this is the analysis of the net pressure force. Let's move to the gravitational force acting, which is given by the weight component in the direction of flow. That is the blue sine theta, okay? This is the weight direction in the direction of flow, okay, which is simply W sin theta, and based on the geometry, sin theta simply opposite of a hypotenuse, okay. The opposite is simply del z, okay, and you have del s, which is the hypotenuse, okay, and it's minus because as you proceed in the direction of flow, the elevation drops, okay, so you have minus sign because del z del s is going to be a negative term, so to make it positive, you introduce the negative sign, which is this one, okay. Now, this is the analysis of the two forces, the gravitational force as well as the pressure force acting on the fluid element. Of course, we have other internal forces within the element, okay, such as the viscous force, okay. Other internal forces acting within the element are expressed similarly in terms of the slope multiplied by the weight of element. You can see this is W del Z del S, this is W gamma del P del S, so multiply W called del H del S, okay. Now, equating all these forces must be equal to MA, okay. Okay, so we sum them up. This is MA, okay. This is the pressure force, okay. This is the gravitational force, and this represent all the other internal forces acting within the element, okay. And when we equate this, we can simplify this later because you can see ds is common all through, so we can knock ds out, okay. Del s is common, okay. So, and you can also see the weight of the fluid element is common, so we can also knock the weight out, okay. And we will be left with the equation below. So this is a simplification, and we can rearrange it further. This can be rearranged further because this is a differential form of the energy equation, which can be integrated, okay. This we can integrate it further to have this equation, okay. It is integrated further, we will have this equation, okay. Which is v squared over 2g plus p over gamma plus z plus h equal constant. This is known as the energy equation, including the internal loss of energy between the two sections. This is the internal loss of energy because as fluid is flowing, it loses energy. So this is called, which is the head loss. We call it head loss, HF. Okay, and the head loss, as we are going to examine later in chapter 15, the head loss is mainly due to the friction. Okay, it's due to the friction. Friction is the major head loss for fluid flows. Okay, so that's why you have HF. Okay, frictional head loss. Okay, of course we have minor losses which we are going to expatiate more in chapter 15. Okay, so we have losses due to bends, enlargement and all that. So we will examine all this and due to appurtenances and all this, okay. So we'll examine each of these minor losses, but the main head loss for fluid flowing, for during fluid flow, is the frictional head loss, okay. So the head loss is given by H2 minus H1, okay? H2 minus H1. So the form of the energy equation is now given as, that is including the head loss, in this case, which is H2 minus H1, okay? So we now have HF here, okay, which takes care of the head loss occurring. Z is the elevation, okay? Pu, in Bernoulli equation, the internal energy term HF is ignored, okay? In Bernoulli equation, we ignore the head loss, okay? So Bernoulli equation, we have only this, okay? We have only these terms, okay? While for the energy equation, which is more more realistic, more practical, okay? Because fluid, as it flows, it loses energy, okay? So for the energy equation, you have additional term in form of HF, which is the frictional head loss. Now, for channel flow, the pressure is gamma Y, which is like rho GH, okay? And the pressure terms in P2 over gamma, Py, P1 over gamma are replaced by depths, okay? Because they simply represent the pressure head, okay? Simply represent the pressure head. So Y1 and Y2 simply represent the pressure head. And the various forms of energy in open channel flow are shown in the figure below. Okay, if you look at the figure, we have two sections depicting all the various terms in the energy equation. Okay, you have the velocity head, which is V squared over 2G. It's called the velocity head. Okay, you have elevation head, you have the pressure head. Okay, and the total gives the energy of the fluid, because as fluid is flowing, it has energy that is pushing it. Okay, and that energy is given by all the summation of these terms. Now, this energy, as it is flowing, is reducing. You can see that this is the channel bottom slope, S naught. This is the weight component, okay, the weight acting vertically downward, and then it has component W sin theta and W cos theta. And you have the water surface or hydraulic grade line, SW. Yeah. You can see that. Hello, doctor. Doctor. Yeah, I'm in the class now. Okay. Thank you, doctor. Okay. So you have the water surface or hydraulic grade line, that's W. You can see that the height of the water surface is gradually reducing as the flow progresses, while the velocity head is increasing, as well as the head loss. Okay, as well as the head loss. The total energy is the top, okay? The total energy in the system remains the same, as we know from the law of conservation of energy. Energy is neither created nor destroyed, but can be transferred from one form to another. The total energy in a system remains the same, okay? But there is transfer of energy. Obviously, you can see from the pressure head, the pressure energy, okay? The pressure head, the energy in the pressure head is being transferred into the velocity head and the frictional head loss, okay? Because as it flows, and this is the energy line slope, okay? SF, the energy line slope, okay? Which is decreasing, but it's being compensated, not losing. We don't lose the energy. The energy loss from the energy slope, okay, is what accounts for the head loss, okay? It's what accounts for the head loss. That's what accounts for the head loss, and head loss can be computed, okay? Now, let's take a simple example to demonstrate this, to demonstrate the Bernoulli equation. Here it says, determine the per unit width of a broad crested weir. Determine the discharge per unit width of a broad crested weir shown in figure 9.4. Disregard the losses. So here we are neglecting the losses. The losses will be in form of HF. So we are disregarding them. Loss term be equal to 0. It will not feature in the equation. Hence, we'll just use the Bernoulli equation. Okay. Now, applying the energy equation at points 1 and 2. Remember, I want to find the discharge per unit width. So applying the energy equation at point 1 and at point 2. Point 2 is in the center of the weir, and disregarding the velocity approach at point 1. Okay, we have normally you have this velocity of approach. You can see it, okay? It is more pronounced at the other section, okay, because it increases. The velocity of approach increases as you move downstream. Okay? More often than not, to simplify the computations, okay, usually we neglect the velocity of approach. Although, as we are going to see in the next chapter, I think chapters 17, we will see that, no, chapter 13, in some of the examples, we will include the velocity of approach and see how our results are affected, okay? Here, we will neglect the velocity of approach. And this is the equation, energy equation. So let's analyze term by term, okay? We are neglecting the velocity of approach, so this gives 0, okay? And it is horizontal, rectangular, okay? So at this point, this is the datum, okay? So Z is equal to 0, okay? And Y, the depth of flow in this case is equal to 10, okay? So this is the datum. So Z1 is equal to 0, okay? But at the second section, Z2 is not equal to 0, it's equal to 4, okay? The depth of flow is equal to 3, okay? And then we have the velocity of the velocity term, the velocity head term in this case. We neglect the approach, the velocity of approach. And in this case, we found V. Once we find V, we can find A, okay? Or we can find Q, because Q is equal to AV. Here it says per unit width, okay? So it's a rectangular channel. Crystal rectangular channel, the area of rectangle is BYA, okay? So Q is equal to capital Q of B, okay? Is the flow or discharge per unit width, which is equal to A times Y, okay? So now we just multiply, sorry, not A times Y, but Y times V, okay? So I have Y to be 3, so per unit width. So we are taking the width B to be equal to 1 feet, okay? And then this is the velocity, which we found from the energy equation. So this is 42 cubic feet per second and per feet width, okay? And the coefficient of discharge, CD, has not been included in the computation, okay? The coefficient of discharge has not been included in the computation. Now, let's analyze further. Here, we have steady flow. It means the flow rate is constant throughout. Okay? The flow rate is constant, and we have a weir. Weir is a hydraulic structure, okay, which we use in discharge measurement, because in open channel flow, one of the most important parameters to determine is the flow rate, okay, the flow rate and the velocity of flow. Okay, because once we know the flow rate, knowing the cross section, we can easily find the velocity. Okay, because these two, the flow rate is very, very important, because as I highlighted earlier in chapter 1, when discussing water resources development, okay, when planning for any water resources development, you have to analyze your need, the need of the community, the water demand. If you remember, we talked about the per capita water consumption, okay? That is the demand, okay? Given the population, what is their per capita water consumption, and then we can find the total water demand, and then we look at available water source that can fulfill or satisfy the water demand of the community, okay? So depending on the water source, normally, like I mentioned, sometimes you can have a river, a stream, groundwater, and all that. Here in Saudi Arabia, we have enormous groundwater resources, but we don't have surface water resources. I mean, in form of, let's say, lakes, rivers, and streams. However, we do have enormous resources or surface water resources in form of seas and oceans surrounding us. Okay, so that's why we use, the seawater desalination. We desalinate the seawater for the municipal water supply. Okay, but we don't have rivers, lakes, streams. Okay, but in other places, in other climes, other countries, you have rivers, streams. Okay, all these are used for water. I mean, for municipal water supply. Okay, and to ensure that water is adequate or the flow will be able to satisfy the demand of the inhabitants, flow rate is very, very important, because it is from the flow rate that we can determine, okay, what is the flow rate per day, per month, per annum, okay? And then we look at the water demand. The water demand, which is also in terms of usually like a flow rate, liters per capita per day. So you have the average water draft, the daily water draft, the hourly water draft, okay? Okay, and all these are in form of flow rate. And then you can now compare, now see, is the flow rate from that stream or river or channel or whatever it is it going to satisfy the water demand? So knowing the flow rate is very important. And as we are going to see later, we use hydraulic structures in measuring the flow rate, because for small channels in the laboratories, we can easily measure the flow rate using some equipment like what we call to measure the velocity, or sometimes we even have the flow rate already controlled, because we use pump, which are graduate, I mean, which gives us the flow rate, okay? But when you have enormous rivers and streams, you don't have that capacity, okay? But we can construct hydraulic structures, and then we can come up with some relationship to determine the height above the hydraulic structures and convert the height to flow rate. This is one of the hydraulic structures we have, which is broad crested weir. Okay, this one is called broad crested weir. It is called broad because this is the crest. The crest is the height over which water flows. Okay, so this is the crest, and you can see it is wide, and broad. So that's why it's called broad crested weir. Okay, and when water flows over it, the cross-sectional area, the effective cross-sectional area of flow is decreased. You remember Q equal AV, which I explained before. For section 1, let's look at A1, A2. Now, you can tell me which area is bigger, which cross-sectional area is bigger from this. Okay, I want all of you to respond. Section 1 or section 2, which of them will have a bigger cross-sectional area of flow? Okay, section 1. Okay. Only 3 have responded so far. Yeah, I said between section 1 and section 2, which one will have higher cross-sectional area of flow? Okay, so you have A1 and A2. So which one is bigger? Is it A1? Is it A2? Are they the same? Okay. Okay, so I think we have all. Okay, let me take it to the presentation mode. So yes, you are correct. A1 has higher cross-sectional area of flow. Okay, but then Q is the same. To maintain the same discharge Q, the velocity has to. Now, what will happen to the velocity at point 2? This is V1. This is V2. Which one is bigger between V1 and V2? Which one will be larger? Which one will have high? Which section will have larger velocity? We don't have point 3. We have only point 1 and 2. Amjad. Okay, point 2. Okay. Abdulaziz. Okay. What I'm saying is that between point 1 and 2, the first question was which one will have higher cross-sectional area? Okay, and most of you just correctly chose that section 1 will have higher cross-sectional area. So now I am now asking which of these points, which of these sections will have higher velocity? The fluid velocity is higher. Which of these sections? Section 1 or section 2? So this is the question. Okay, section 2. All right, let me go back to the presentation mode. Now, yes, you are right. Section 2 will have higher velocity. But why? Okay, why? Because 2 equal AV. A1 V1 equal A2 V. Okay, A1 here is higher, so while A2 here is smaller. Okay, so V1 here is smaller, but V2 here is higher, so that A1 V1 equals A2 V2. So the flow is accelerated. What I'm saying is that the hydraulic structure here, which is a broad crested weir, accelerates the flow. Okay, it makes the flow run, it goes faster on the crest. Okay, so when it goes fast, the velocity increases and the cross-sectional area reduces. But the flow rate Q remains the same. Q1 is equal to Q. Okay, so flow rate remains the same. This we will test in the lab. Okay, specifically, this we will perform in the lab and we will analyze it. Okay, but then to measure flow rate using the weirs, you need to calibrate it. You need to calibrate because all we need to do, like in this case, is to measure the head above the crest. Okay, and then we go and find a formula where we convert the head to flow rate. Okay, but then we realize that there is what is called coefficient of discharge. Okay, for all the hydraulic structures, they need to be calibrated. You need to know the coefficient of discharge of the hydraulic structure, and the coefficient of discharge is simply the theoretical flow over the actual flow. Okay, it's simply a ratio of the theoretical flow over the actual flow. The theoretical flow, you see, when deriving any formula and what have you, we make a lot of assumptions, ignore certain things. Like in this case, we ignored the loss. Okay, in this example, we ignored the loss. Okay, we disregard all losses. So this will give us the theoretical flow rate. Okay, so this flow rate we determine is theoretical. If we want to find the actual flow rate, if we want to go to the field and measure the flow rate, and then when we calculate it, it will give us exactly what we measured in the field. Then we need to find the actual flow rate. Okay, and the actual flow rate is now equal to the coefficient of discharge times the theoretical flow rate. Okay, how do we find the coefficient of discharge? We go to the lab. Okay, we go to the lab and measure, the heads at different preset discharge, and then make some measure and then fit in the equation, okay, to find the coefficient of discharge using the theoretical flow rate, and then Once we find the coefficient of discharge, at any time we want to get the actual flow rate, we only multiply the theoretical flow rate by the coefficient of discharge. So in this case, this comment that the coefficient of discharge CD has not been included in the computation. It means that the flow rate that we obtained, that's the discharge per unit width, is the theoretical discharge, okay, not the actual discharge. Meaning, if you were to simulate this flow in the lab and try to measure the discharge, you will realize that the discharge is less than 42, because all the time you realize the theoretical this flow rate is greater than the actual flow rate. Because in the theoretical flow rate, um, the theoretical flow rate is usually smaller than the actual flow rate. Okay, it's smaller because all the time when deriving equations, we have our set of assumptions. We normally have our assumptions, and in those assumptions, we normally try to neglect the effect of certain terms. We neglect these terms to simplify the derivation and the computation. Okay, so that is why you realize that the theoretical discharge is usually smaller than the actual discharge, because the coefficient of discharge is usually less than 1. Okay, if it is less than 1, it means that the denominator is okay, sorry, this is QA, this is QA over QT. Okay, QA over QT. Yes, so that the actual flow rate is CD times QT. Okay, so the coefficient of discharge is QA over QT, and CD is always less than 1, then it follows that QT is always greater than QA. Sorry, I interchange QT with QA. So the theoretical discharge is always greater than the actual discharge, and this is because of overestimation. Because in the theoretical derivation, we normally neglect and ignore certain terms. Like in this case, we ignore the frictional head loss. Definitely, it's not equal to 0. Definitely, it is not equal to 0. But for simplicity of computations, we neglected the coefficient of the losses, the frictional head loss. Of course, there are a lot of other assumptions that lead to the oversimplification of the theoretical computation, okay, which in the actual discharge, it will give you the exact value, taking care of all the factors affecting the flow. Okay, so that is why the theoretical flow rate usually overestimates, meaning it gives higher than the actual value. Okay, the theoretical flow rate usually gives higher than the actual value, meaning if we are to go to the lab and get this flow and measure the flow rate, it's going to be lower than 42 cubic feet per second per feet width. Okay, this is going to be lower because the actual flow rate is usually lower than the theoretical flow rate. Okay, and how do we adjust? The coefficient of discharge takes care of all these assumptions, okay, of all these assumptions that were made in the derivation of the theoretical discharge. This will expatiate more in the next chapter, okay, which is going to be on the hydraulic structures. But this is just like a preamble, like an introduction to it. Okay? And this is why it is mentioned here that the coefficient of discharge has not been included in the computation. Because definitely, if it is included in the computation, we will have um, lower flow rate. Okay, because the coefficient of discharge is usually less than 1. So when you multiply the coefficient of discharge with the theoretical flow rate, then the actual flow rate is going to be less than the theoretical flow rate. I hope it is clear. Now, let's take some break before we start the momentum equation. Okay. Yes, welcome back, gentlemen. Let's move on. Okay, so the momentum equation. Here, in the previous one, we used MA, and yeah, here we will use the momentum, okay, and the resultant force on a fluid element is also equal to the change of rate of momentum. The previous case we use MA, isn't it? Okay, that resultant force on a fluid element is equal to mass times its acceleration. Okay? Here we are saying that the resultant force, okay, on a fluid element is equal to the rate of change of momentum, which is also from the Newton's second law. Yeah, it's also from the Newton's second law of motion. We all know that momentum is simply the product of mass and velocity. Okay, so the rate of change of momentum is mdv dt. Okay, and in figure 9.2, we have the forces acting on the element, which are the net pressure force and the gravity force. Okay, so here we will use the momentum equation. Okay, uh, the friction force acts along the surface of contact between the uh, water and channel bottom. So this is the same figure that we worked with previously. Okay, when there is a lateral inflow, momentum transfer due to lateral inflow should be included as well. The equation is developed as follows. So it's pretty well similar to how we generated the energy equation. We have the pressure force acting. Okay, this phase, that phase, we have the weight whose direction in the direction of flow is W sin theta, okay, and W is given by rho G A delta S, okay. Now, for a fluid of mass m and velocity v, the change of rate of momentum is mdv dt, okay. The velocity term can be expressed, which is dv dt, can be expressed as del v del t plus v del v del s, okay. This we did in dynamics. Okay, as the rate of change of momentum consists of two parts. Because if this is the velocity, then we have md del v del t plus mv del v del s. Okay, so the rate of change of momentum consists of two parts. The change of momentum with respect to time, which is m del v del t, okay, referred to as temporal or local acceleration. And we have the spatial change momentum because we have mv del v del s. Okay, so del s is the convection acceleration, okay, which is the spatial change of momentum. Spatial meaning with respect to distance, okay, the change of momentum with respect to distance. Temporal, the change of momentum with respect to time. Temporal referring to time, and spatial referring to space, distance, okay. Now from the figure, the net pressure force, okay, this is the net pressure force, okay, or W dy ds, okay. That's the pressure. If we look at it very well, P equal to rho G AY, okay, and rho G AY, and this simplifies into, since, okay, it's even here, the pressure force, capital, we use the capital P to represent the pressure force and small p to represent the pressure itself. So don't be confused with the notation. Okay? So the capital P here is the pressure force, okay, which is gamma y. Gamma is the pressure, okay, small p times dA. okay, which gives the pressure force, okay, and then you now have W is what? Unit weight. I mean, yeah, the specific weight, which is weight per unit times the volume. Okay, delta A times delta S. Delta A times delta S. Okay. So you can see here clearly that the pressure force is simply, when you substitute, because gamma simply 1, and then here you have, when you replace gamma delta A, so this will be W over delta S. Okay, okay. That is substituting gamma delta S into this, and then del P del S. Let me do it this way. P now is Y W delta S over del S times delta S, isn't it? Okay. So the only variable here is Y. So this will come out and cancel that. So we will have minus W del Y del S, which is exactly what we have here. Okay. Now the gravitational force is given by the element weight component in the direction of flow, which is W sin theta or WS naught. Okay, S naught being the channel slope. Okay, S naught is the channel slope. Angle of inclination, okay, is theta. Okay, so the channel slope is S naught. Now we also evaluate the friction force. The friction force along the bottom is equal to the friction slope multiplied by the weight of the element. Okay, that is WSF. Okay.
Did you send appointment letters for the GAs to Dr. Wahab?
Yes, it's in the appointment letters. I even showed you there's the appointment letters as well as the approval for the scholarship. Yes. Okay, then I will. You didn't inform me like that Excel. No, I showed you in the system. Yeah. No, for all.
Can you see them all?
No. I attached all in zip file. So I sent everything to him. But then he said there was one file, the Excel file, that was missing. So he sent me back, and then I sent again. So I didn't know he did not have this. But I showed him in my system, all of them. No, it is there. It is there. Okay. So once I'm done now with my class, I will send it to you.
Okay, sorry for interrupting.
Sorry for the interruption. The dean came for some urgent information. All right, let's move on. The friction force along the bottom is equal to the friction slope multiplied by the weight of the element, okay, which is WSF, okay. So here, equating all the momentum terms, one, A and B above with external forces, okay. So the rate of momentum is equal to now all the forces acting, okay. So this is the pressure term, this is the gravity term as a result of the weight, and this is the friction term, okay, which is minus in the opposite direction. The gravity term is in the direction of flow, Okay, so that's why it's positive. Okay, and the pressure term is negative because the pressure reduces with distance. Okay, that's why it's negative. And the friction term is in the opposite direction, is opposite to the direction of flow. Okay, and this is the rate of change of momentum, which is simply ma. This is m. Okay, this is simply the dv dt. Okay, which is the which represents the acceleration. Okay, which is called the inertia term. Now, equation 8.9.7 is the momentum equation. Okay, the term WSF measures the force exerted by the water. Okay, the force exerted by the water. It is not related to internal losses. Many applications, this can be omitted. Okay, so this can be omitted. It's not related to the internal forces. It's referring to the force exerted by the water. Okay? Uh, And then for steady state, we have the velocity not changing with respect to time, because steady means time is fixed. I mean, the flow properties do not change with respect to time. Hence, any variation with respect to time will be eliminated. And here we have dv dt. Okay, so this term will be 0. Okay? And this equation will reduce to the discrete form of this, which is rho A Vn Vs 2 minus section 1 equal summation Fs. I will explain each of the terms below. Okay, the subscript 2 relates to the outflow section. Okay, subscript 1 refers to the inflow section. So, like you have inflow upstream and downstream. The subscript S denotes the direction, such as x, y, or z. That is the direction of flow to which the momentum equation is applied. And Vn is the velocity normal to the flow. Okay? Vn is the velocity normal to the flow. Okay, and Vs is the velocity component in the S direction. Usually these are the same. Okay, normal to the flow in the direction of flow. So then you will end up with V squared. Okay, and then the outflow vector, the outflow velocity vector, Vs denotes the positive direction with reference to the signs, with reference to which signs are assigned for all terms. That is the flow direction. The term summation Fs denotes all applied forces. The change in momentum, this is the change in momentum at 0.2 minus 0.1, okay, is equal to the summation of all the applied forces. That is the pressure force, the weight, and the friction term, okay, which we neglected. Okay? So here we have the pressure force, which is P minus P2, and the weight component in S direction, and other applied forces. Now let's look at a simple example to demonstrate the application of the momentum principle. And here we are to resolve the problem we solved using the energy equation by the momentum principle. At the beginning, we mentioned that many problems you find that you can apply, both the energy equation and the momentum equation to solve the same problem. But there are some problems probably you may only be able to apply maybe one of them to solve it. Okay. Now, figure 9.5, this is the figure. Example 9.1. That is this figure. Okay. This figure. So now we want to find the flow rate per unit width. Okay. But now, considering the horizontal bed, the weight component in the direction of flow is 0, because the weight will be horizontal in that case. It will not have component. It will not have horizontal component since the bed is horizontal. So the bed is horizontal, so the weight component will have only that component. Okay, if it were inclined, if the bed were inclined, okay, that is when the weight component, this is the vertical component W, but there you'll have component in the direction of flow. Okay, because this is angle theta, so this will be W sin theta, this will be W cos theta. If theta is 0, then the weight will only be vertical, okay? No horizontal, no component in the direction of flow. Component in the direction of flow will be 0. It will only be vertical, okay? So this is what the first statement is implying. And then pressure force is acting. So we need to analyze the pressure forces acting. So here we have eliminated the weight component. So the pressure forces acting, we have at the upstream phase, section 1 and section 2. But before analyzing the pressure forces acting, because these are hydrostatic pressure force, hydrostatic forces, let me go back to the to explain hydrostatic forces in the next slide, and then we will come back. Okay? This figure here, I want to analyze the hydrostatic forces acting on a plane surface. Okay, a plane surface form a pressure prism whose base left face is the surface and whose length is the pressure. When you have something immersed in water, let's say AB, the pressure acting, of course, it will increase with depth. Okay, this is because of the atmospheric pressure. So this is the absolute pressure, but if you want it to be gauge pressure, so it will be from here. Okay, it will be triangular rather than trapezoidal. Okay, it is going to be triangular rather than trapezoidal. So now, in this case, this is the pressure acting on the face, on the area AB. Okay, now the pressure acts normal to the surface, and the hydrostatic forces on a flat plate of any shape form a volume whose base is the plate. Okay, so the hydrostatic forces acting on any plate, okay, of any shape forms a volume whose base is the plate area and whose length is the linearly varying pressure. So this is the linearly varying pressure. You can see it, okay? At the, no, here is not 0 because it is not at the surface, okay? So let me, if it were to be at the surface, because when you have atmospheric pressure acting, that is when the pressure is 0. If we take atmospheric pressure to be the reference pressure, okay? So this is the pressure, okay? Okay, on the whole volume. And how do you find the virtual pressure prism has an interesting physical interpretation. Its volume is equal to the magnitude of the resultant hydrostatic force acting on the plate. The volume of this prism is the resultant hydrostatic force. And how do we find the volume? Okay, how do we find the volume? Okay, in this case, it is going to be integral of PdA. If we are to find the area of this trapezium here, okay, and multiply by the breadth A, that will give us the volume, and that will give us the resultant pressure force. If it is on top, like here, okay, so if it is on that surface where you have atmospheric pressure acting, so in that case, you have the 0 pressure at the top because atmospheric pressure is taken as the reference pressure, which is 0. So each pressure increases linearly down, okay? So it's going to be the area of the triangle times the breadth, okay? Now let's go back. Here, now this is the hydrostatic pressure acting, because this is top of this is the water surface, so you have triangular hydrostatic pressure distribution. Okay, at the top is 0 because you have atmospheric pressure acting. Okay, so we find the area, and this is the height y1. So this is the pressure. The pressure here is gamma y1. Okay, and y1 is 10, so that's why you have 10 gamma. Okay, so to find the pressure force P1 is going to be the area here, which is the area of the triangle, which is half gamma y1. So this is gamma y1 base times the height is y1 also. Okay, so this is the area. And because we want to find the volume. The volume gives the hydrostatic pressure times the breadth, which is B. Okay, so this will be half gamma y1 squared B. Okay, so that will give us the pressure force P1. Okay, the same. Okay, then let's go back. That's exactly what we have. Half P1 is half gamma B y1 squared. Okay, and B is 1, gamma B is 1, Y is 10. So P1 is equal to 50Y. Okay. Now for section 2, we do the same thing. This is section 2, and the pressure is hydrostatic. Okay. The pressure is hydrostatic. If it's hydrostatic, this is section 2. Okay. We have P2. And P2, because Y2 is 3, so the base here is gamma Y2, which is 3 gamma. Okay, so P2 is also given by the area of the triangle. Half base is gamma y2 times height, the height is y2, times the breadth, which is B. So P2 is going to be half gamma B y2 squared also. Okay, which is exactly what we have here. Okay, and then we have our B and y substituted, so this is 4.5 gamma. Okay, and for water pressure on the weir face at section 2, okay, water pressure on the weir face at section 2, which we call P3. Let's go so that you see it clearly. So the water pressure on the face of the weir here, okay, this is the face. So it's also hydrostatic and it rises up to the height of the weir. Okay, so that's why we have the pressure acting up to this. Above it, we already have taken care of this, which is represented by this one. Okay, but then we drew the complete triangle to simplify our analysis. That is up to the height here, up to the upstream height at section 1. So now at this point, and this is P3, okay, which is the pressure force at point at the face of the weir. Okay, so at this point, because it's similar to this one, okay, so the height is also 10, so we have 10 gamma similar to this one. Okay, but here we have 6 gamma. And how did we arrive at 6 gamma? I will take you through it. Okay, here we have y1 minus h. Okay, y1 minus h. This is y1. Y1 minus h. Y1 is the depth, the total depth. H is the height of the weir. Okay, so when you subtract this depth, so this is now y1 minus h. Okay, we know what is Y1, we know what is H, okay? 10 minus 4, which is 6, okay? So how can we find the pressure at this point? Pressure at this point, we can find it by using similar triangle, okay? By using similar triangle. And to do that, this side over that side is equal to this side over this side. Simple, because they all have the same angle. This angle theta is common to this small triangle and is common to the bigger triangle. So the sides are also proportionate. So that means 10 gamma, which is this side, over the depth y1. Let me say 10, yeah, which is 10, is equal to this side, let me say x, which is what I want to find, divided by this one, which is 6. Okay, the 10 cancels out. We have now x equal to 6 gamma. So that is how we obtain this 6 gamma here. Okay, and to find the pressure distribution is simply the area of the trapezium times b. We explain y times b, okay? Because the pressure acting is the volume. Okay, the pressure force acting is the volume. Okay, the volume of the prism. Okay, which is simply the area in this, like in this case, is going to be the area of this. Okay, times b. Okay, simply b times area of pressure trapezoid. Okay, and trapezium, the area of trapezium is half sum of parallel sides times height. So that's why you have half sum of the parallel sides, 6 plus 10, times the height, which is 4. Okay, these are the parallel sides, 6 gamma plus 10 gamma. So the area of trapezium is half sum of the parallel sides, 6 gamma plus 10 gamma, times the height. The height is 4. Okay, that's exactly what you have. Okay, this is 32 gamma. Okay, don't forget, gamma is a constant, is the unit weight of water. So if we want to find the exact pressure forces, we will simply substitute gamma. Okay, now obtain forces applying the momentum equation between sections 1 and 2. Okay, we now have to section 2 minus section 1 using this formula. Okay, this formula. Okay, so a okay, so now at section 1, no, this is at section 2, okay, because this is the area, okay? This is v2 squared, because Vn, the normal velocity, is equal to the velocity in the direction of flow, which is Vs, okay, and this is gamma over g, okay, because density, gamma is equal to rho g, so density is now gamma over g, okay, so this is rho, okay, at point 2, v2 squared, okay. At point 1, we have the depth to be 10, and then the breadth to be 1, okay. In both cases, the breadth, we are considering unit breadth. So the change in momentum, this change in momentum, that is the change in momentum at section 2 minus that of section 1 is equal to the algebraic sum of all the forces, okay. These are the pressure forces, okay, acting. We already explained that the gravitational force is 0 because the channel bottom is horizontal, and the weight component in the direction of flow is 0. Okay, so yeah, I think this is P1, P2, and P3. Okay, P1, P2, and P3. Okay, and then of course, yeah, the only unknown from the continuity equation, A1 V1 equal Q equal A1 V1. Okay, so V1 is equal to Q over 10. Okay, the same thing, we can now generate expression for Q, V2. Okay, in terms of Q, because this flow is continuous, and A1 V1 equal A2 V2. So in terms of V2, V1 is equal to Q over 10, V2 is Q over 3. So we go back here to substitute for V1 and V2 so that we can find Q. Okay, so you can see that we almost got the same thing. I think in the previous example we got around 42. Okay, and these are the differences is due to the assumptions specifically disregarding the velocity of approach. Okay, because in the previous example the velocity of approach was neglected. Okay, but in this case we have we did not neglect anything here. In the momentum equation, it does not involve the velocity. We involve the approach velocity in this case, okay, which was neglected in the previous computation. Okay, so in the previous example, using the energy equation, we obtained 42, I think, 42 cubic. Yeah, 42 cubic feet per second per feet width. Okay, yeah, we've got 43. Okay, I hope it is clear. Okay. Yeah. Any question? All right, see you in the lab. We will take our third quiz today, okay? Which is in chapter 5, that's groundwater flow. Okay? Bye-bye.